In this research paper titled Disentangling Linguistic Features with Dimension-Wise Analysis of Vector Embeddings, authored by Sania Karwa and Navpreet Singh from the Massachusetts Institute of Technology, the focus is on unraveling the mysteries of neural embeddings, particularly in models like BERT. These embeddings are high-dimensional vectors that represent words or sentences in a way that machines can process, but their complexity often makes them hard to interpret, like looking into a black box. The paper begins by highlighting the evolution of word embeddings. Early models such as Word2Vec and Glove laid the groundwork by mapping words to vectors based on their co-occurrence in text. More advanced models like BERT, which uses bidirectional transformers, take this further by creating contextualized representations that capture both syntax and semantics. For instance, BERT can understand how the meaning of a word changes based on the surrounding words in a sentence. Despite these advancements, the high-dimensional nature of these embeddings, often hundreds of dimensions, makes it challenging to pinpoint exactly what each dimension represents. To address this, the authors propose a new framework aimed at identifying which specific dimensions in these vector embeddings encode distinct linguistic properties. Linguistic properties, or LPs, are fundamental aspects of language like synonymy, which deals with words that mean the same thing. Negation, which involves words like not, that flip the meaning, tense, which indicates time such as past or future, and quantity, which relates to numbers or amounts. They also include other features like intensifiers, which amplify meaning, voice, which shifts between active and passive forms, definiteness, factuality, and polarity, which covers positive or negative sentiments. A key contribution of this paper is the introduction of the Linguistically Distinct Sentence Pairs dataset, known as LDSP-10. This dataset consists of pairs of sentences carefully designed to isolate and highlight 10 specific linguistic properties. For example, one pair might compare a sentence with a synonym substituted versus the original, while another might flip negation to see how it changes the embedding. By using these controlled sentence pairs, the researchers can probe the embeddings and determine which dimensions are most sensitive to each property. The analysis involves several statistical methods to examine BERT embeddings and those from other models like GPT-2 and MPNet. First, they apply the Wilcoxon signed rank test, a non-parametric statistical test that compares the distributions of values in different dimensions between sentence pairs. This helps identify if certain dimensions show significant differences when a linguistic property is altered. Next, they use mutual information, a concept from information theory that measures how much one variable tells us about another. In this context, it quantifies how much information about a linguistic property is contained in each embedding dimension. Additionally, they employ recursive feature elimination, a technique that systematically removes less important dimensions to find the most influential ones for each property. From these analyses, the authors introduce a new metric called the Embedding Dimension Importance, or EDI score. This score aggregates the results from the statistical tests and mutual information to provide a single, quantifiable measure of how relevant each dimension is to a specific linguistic property. For instance, an EDI score above 0.8 might indicate that a dimension is highly important for encoding negation. The paper presents findings from applying this framework to BERT, GPT-2, and MPNet embeddings. They discovered that some linguistic properties are robustly encoded in specific dimensions. For example, negation and polarity tend to be concentrated in particular dimensions, making them easier to identify and manipulate. In contrast, properties like synonymy show more complex patterns, spread across multiple dimensions, which suggests that not all linguistic features are encoded in the same straightforward way. To illustrate these results, the paper includes a figure that visualizes the dimensions of BERT embeddings with the highest EDI scores for each linguistic property. It shows, for instance, which dimensions are most relevant for tense or quantity, based on thresholds like an EDI score above 0.8. There's also a table that evaluates the accuracy of a simple logistic classifier when trained on the most important subsets of dimensions from each model. For BERT, accuracies range from around 0.50 for control properties up to 0.99 for negation, demonstrating that even a basic classifier can perform well when focusing on these key dimensions. Similar results are shown for GPT-2 and MPNet, with GPT-2 achieving high accuracies for quantity and voice, for example. This work builds on related research in interpretable embeddings, which can be divided into categories like developing models that are inherently more transparent or analyzing existing ones to extract meaning. The authors position their framework as generalizable, meaning it can be applied to other models and linguistic features beyond those in the LDSP-10 dataset. The implications of this study are significant for the field of natural language processing. By identifying which dimensions encode specific linguistic properties, researchers and developers can create more transparent language models. This could help in mitigating biases, as seen in cases where embeddings inadvertently perpetuate stereotypes. For instance, if a dimension is found to encode gender bias, it could be adjusted or removed. Additionally, this approach allows for task-specific optimization, where models are fine-tuned to emphasize certain linguistic features, improving performance in applications like sentiment analysis or machine translation. Finally, it enhances system controllability, enabling users to manipulate embeddings for more precise outcomes, such as generating text with specific tones or factual accuracies. Overall, this paper provides valuable insights into the structure of neural embeddings, paving the way for more responsible and interpretable AI systems in language processing.